pleasure. Honor.
Students are being slow.
Yeah, let's wait perhaps 1 minute.
As soon as we start, everyone will come in.
No, I think we can start.
Okay, so this morning we have Riccardo Rattazzi starting his lectures on particle physics for string theory.
Thank you. So first of all, thank you for inviting me to give these lectures. One first comment: the title is not a title that was chosen after thinking. It just came up as a joke, and it stuck. Okay, so I'm here presenting an apology of my discipline, call it Beyond the Standard Model, in front of the future leaders of string theory. So let's, before being burned at stake, then let's wait, let's see how much fire. So, in fact, a possible title of this course could have been Behind and Beyond the Standard Model. Okay, and as I will explain in a moment. So, quantum field theory. As we are approaching the 90th birthday of quantum field theory, we can only reckon how our progress in understanding of fundamental physics over the last 90 years has really gone hand in hand with the progress in our theoretical understanding of quantum field theory. The crown jewel, the coronation of this process is the Standard Model, a specific quantum field theory that beautifully, remarkably accounts for a multitude of experimental data that have been collected in collider, particle colliders over the last 40 decades. And in some respects, the Standard Model is really remarkable. I mean, it has level of precision that were not expected when I started doing physics 30 years ago, but it does. So, but what is perhaps even more remarkable is that side by side at these successes of the Standard Model, there lie mysteries, paradoxes, and tantalizing hints on what could be behind it or beyond it. And I don't need to tell you what these mysteries and paradoxes are. The one and the foremost is that we basically don't understand space-time. We don't understand why we live in a flat and big universe. The zeroth order the first computation you do in quantum field theory when you quantize the Klein-Gordon field, the vacuum energy. Of course, you find out that it's not calculable, but if you have to guess what the result would be, assuming that someday you would be able to calculate it, you would be completely orders and orders of magnitude away from what you really observe. So it's the first computation in quantum field theory. So when you present it, first you have to encourage students, wait a moment, and there is also G-2, there are other things. But for a while, it's not easy to keep there. If you're honest, okay, if you insist on saying that, of course, if you just say, okay, you don't say it, nobody will realize in the first lecture, okay? That's precisely quantum field theory. And then of a similar nature, the hierarchy problem or the hierarchy paradox. Again, I don't need to tell you. We don't know what the matter that makes the vast majority of the matter that exists in galaxies is made of. And Mariangela is guiding us through progress towards trying to figure that out. And there are also, these are all the mysteries and paradoxes. And there are also tantalizing hints, okay? There are really features of the standard model that speak to us about the fact that we are really missing something, that there is a structure that is interesting. Take, for instance, gauge interactions, okay? Ordinary gauge interaction, not gravity. It could have happened that the couplings at ordinary energies, say at the weak scale, were different by a factor of a few with respect to what we really observe. And given that the fact that the couplings evolved logarithmically, it could have been that the couplings never came even approximately close when you extrapolate above or below in energy. As a matter of fact, instead, the couplings are chosen by nature in such a way that they do come very close, within, say, 20%, even in the standard model. And that happens, remarkably, at an energy scale that is not so much far away from the energy scale where gravity becomes also important and comparable in strength. It could have happened 80 orders of magnitude above or below. Okay, it happens there. So there is an indication. And very much there are similar indications in the structure of Yukawa couplings and so on. And so my opinion, and I think the opinion of the majority of us, is that if progress will be made on all of these questions, progress will likely be will likely force us to go beyond quantum field theory, perhaps along the direction that is being indicated to us by string theory in all its ramifications. I think that's fair, but I think it's equally fair that there's still plenty of space for progress within quantum field theory. Okay, dark matter is certainly a case. Okay, very likely we'll understand dark matter in quantum field theory. We will not need to go to string theory to understand dark matter. I could be wrong, but I think it's very likely we'll understand it in field theory, very much as we have understanding or explanations that may not work about the hierarchy problem within field theory. Okay, we have understanding about leptogenesis in field theory. We have several things. So there is still plenty of work and of possibilities just within quantum field theory. Of course, we have to be open to go beyond. So my lectures have the aim of giving you a perspective on this field of research that tries to attack some of the open problems of particle physics within the context of quantum field theory. This is the so-called physics beyond the standard model domain. And my lectures are basically divided into two parts. Okay, and I'd be very, very happy if I get to do the first part, because I know that I typically misestimate the length of my lectures by a factor of 3. But it depends very much also on how the audience interact and all that. Okay, so the first part, which I would call behind the standard model.
Yeah, sorry, they can't see if it's in the shadow there.
It's behind. So it's okay. So, and the items that I will discuss here are if you want, the effective field theory ideology and naturalness. You need to have an ideology, okay? Doesn't mean this ideology does not need to coincide with truth, okay? You have to be ready to change it, but you need an ideology, okay? Then I will discuss the standard model as an effective field theory. And its praise. I hope I write it correctly. Praise, Z or S? Praise, S. Yes, you're right. Okay. So this is about how beautiful the standard model is. Okay. It's really structurally quite remarkable, and its beauty, the structural remarkability of the standard model has very much to do is in one-to-one correspondence with the effort and the difficulty that people like me are facing in their activity. Okay, and then the third part will be the hierarchy problem, or if you want, the hierarchy paradox. In fact, the hierarchy paradox, it is a paradox because it's formulated as a feature of the standard model. On one side, the standard model is beautiful, and on another side is ugly. And these two sides are very much connected to one another. The beauty and the ugliness are the same thing. This is why it's a paradox. Okay, it may be a question of taste, but and so then there's a second part. The second part is, if you want more standard, is what I call beyond. And here I have a choice, and I could go on and on and on. And so I just wanted to illustrate to you the two major systems that dominate our understanding concerning the hierarchy problem, and this is supersymmetry and compositeness. I think that even if any of these ideas is not realized as a solution to the hierarchy problem, I still think it's worth knowing about them, knowing, appreciate what's wrong with them, how they fail, how they work. So that's okay. So it's not clear to me that I will do everything. Okay, and we will see. Okay, I'll already be happy to do this and part of that. Okay, so let me start. Let me start with the first part. Okay, and today I'll basically discuss the effective field theory ideology and introduce the notion of naturalness and of naturally large hierarchies in field theory. Okay, so here I can write. So since the time of Wilson, but some pragmatic physicists had this idea before. I think Fermi, more or less, was not so much worried about cutoffs, stuff like that. Since the time of Wilson, our viewpoint on quantum field theory is that under basically all circumstances, we should regard a quantum field theory as an effective theory. Valid description, valid below some fundamental scale, physical scale, lambda, that could be the string scale, the lattice length, inverse lattice length. It could be the scale where you match onto another quantum field theory. God knows, okay? But unavoidably, if you have the idea is that a macroscopic quantum system at long enough energy, at long enough distances will be described by quantum field theory. I don't know what are the counterexamples of these, perhaps in condensed matter. Now, with relativity in, I think it's tougher to. So, for instance, you cannot have limit cycles and stuff like that. But this is again field theory. So anyway, let's assume quantum field theory looks like it works. Okay, and so you have here whatever you may have, strings or lattice, who knows, space-time foam, whatever, a new QFT, something else, and then you have all that is possible basically happens. Okay, you have a general Lagrangian, and I'll come back to this comment about all that is possible happens. All that is possible is compulsory later on. That's precisely related to naturalness. And then so you have this fundamental scale, and then you perform measurements at any energy scale or length scale. I mean, energy scale below lambda or length scale longer than 1 over lambda. And I mean, the case we are interested in, we want to focus on, is a case where this effective field theory has a range of validity. Okay, in the sense that if the gap were of order lambda, then that's it. Okay, it's the end of the story. So the scale where our main description will have to be changed to a new one is, let me assume, some IR scale that is much below, or parametrically below lambda. I mean, this lambda IR could be the scale where there could be a gap. It could be the scale where you transit to a new dynamics. It's certainly the scale where the dynamic changes. Okay, you could imagine having it here. If it's a gap, then there's nothing to discuss. If it is the scale where the dynamic changes, then change the dynamics right away and use another effective field theory. So anyway, it's interesting to consider the situation where you have a separation of mass scales. So then, basically by assumption, okay, this situation, what do I have? I have dynamics, okay, that emerges at scale lambda, and the next energy scale where something really changes dramatically is way below. Okay, so what does it mean? That in this range, okay, in the range between lambda and lambda IR, the dynamics doesn't change dramatically. In fact, if you want, it's by assumption, but that's our normal, okay, view of quantum field theory. All the quantum field theories we used in particle physics, okay, we have the standard model, we match to the pi Lagrangian, we match to QED, have precisely this property. There's a physical cutoff, and then the next layer is way below. In the between, the dynamics doesn't change dramatically, which means that the dynamics is approximately scale invariant. Okay, so the dynamics in this domain is approximately scale invariant, if you want, by definition. Okay. Technically, if you, this statement can be phrased with the fact that the dynamics in this range is described by a Lagrangian that corresponds to a fixed point Lagrangian, scale invariant Lagrangian, plus a deformation Lagrangian. And the effect of this deformation Lagrangian are small for in the range. Okay. So we started talking about effective field theory, started talking about quantum field theory. We are already talking about approximate scale invariance. Okay, and you can think of the various effective field theories that we use to describe physics, starting from the Wee scale down, as precisely in these terms. And in those cases, the fixed point Lagrangian is what type of Lagrangian? Free, right? In the cases we are used to, the fixed point Lagrangian is just free. Okay, let me use this. I don't know whether this is good English. But and by the way, okay, so this is the small perturbation normally is dominated by renormalizable couplings. I'll get back to this in a moment. However, it could be that at a certain point when thinking of particle physics problem, we could open our mind a little bit and think of fixed point Lagrangians that are not free. Okay, it's possible. Well, in condensed matter, we have examples. Okay, and we certainly have examples in theoretical quantum field theory. Okay, and so it could be that we have some strongly coupled fixed point. And it turns out, and this is a very interesting and important fact, that in all the cases, in all the relevant cases we know, scale invariance, okay? Whether the scale the fixed point is free or interacting, scale invariance plus Poincare invariance together and unitarity together team up to imply a bigger symmetry that is conformal invariance. Okay, so effective field theory, scale separation, approximate scale invariance, and it's just a fact that scale invariance for Poincare under all circumstances we know imply conformal invariance. Certainly that is the case in 2 dimensions. Of course, I'm not talking about 2 dimensions, and that was first proven by combined work by Sasha Zamolodchikov and Joe in the 80s. Okay, so in 2 dimensions, it's established scale invariance implies conformal invariance. In 4 dimensions, the situation was stagnating for a while. There was progress in the last few years as a byproduct of the proof of the A theorem in 4 dimensions. And well, it depends on whom you ask. They may tell you that it's proven, or well, there's a very strong indication that it's proven, but it's not proven. And certainly, what is certainly the case is that a 4-dimensional theory, a unitary 4-dimensional Lorentz invariant theory that has scale invariant, not to be conformal invariant, would have to be very, very, very peculiar. Okay, there are, and if you want, I can discuss that later on. But so it's.
Sorry, could you say like what more about how
the Well, I mean, you very, 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 very roughly, okay? The A theorem established an irreversibility. There's a quantity that flows monotonically, okay? And the flow of this if the theory is conformal invariant, the flow of this variable is frozen, doesn't flow, stays constant. But if the theory is only scale invariant, this quantity keeps flowing, okay? And if it keeps flowing, quantities will become infinite. And if you assume the quantities are finite, you get a contradiction. But of course, there could be infinities lying behind this, okay? So that's, if you want, a very, very quick and dirty way of saying it. So there is a very strong indication that even in 4 dimensions, we have conformal invariant theories. So in other words, this thing here is this. Okay, so whenever we have an effective field theory is an approximate conformal field theory. So we're studying quantum field theory in a neighborhood of a conformal fixed point. Okay, so the area of the playground of model builders that use quantum field theory to attack the problem of particle physics is this neighborhood around conformal field theory. This is why the studies of conformal field theories are very, very interesting for phenomenologists like me. Okay, speculative phenomenologists, okay? Okay, let me not use the word, I mean, people may get offended, okay? I'm not phenomenology, okay? So for instance, and it's interesting because for conformal field theories, you can say a lot of stuff, okay? You've seen in the talk by Simmons-Duffin. In fact, the statement that scale invariance implies conformal invariance can be made very precise in the neighborhood of a conformal fixed point. So let's say if there is a conformal fixed point, okay, in the region around the fixed point where all beta functions are small, there cannot be a point where the theory is scale invariant and not conformal invariant. Okay, there can be points that are also conformal invariant, like you have in Banks-Zaks. Banks-Zaks, there's a small parameter epsilon, so there's a region very close to the original free fixed point where there's another fixed point, and that's also conformal. It has to be conformal. Okay, that's a theorem. Okay. And similarly, in the neighborhood of a CFT, you cannot have cycles. You cannot have a point where the RG flow keeps cycling. You cannot have strange attractors. You cannot have tori. You cannot have, I mean, in the neighborhood of a CFT, the flow, the theory either flows to another CFT or flows out of this domain. God knows what happens. Okay, I mean, goes to in the domain where you need to change your description. So this is all in the neighborhood of a CFT. Of course, what happens very far away right now, we cannot yet constrain. For instance, can we have cycles that are huge, okay, like this, such a way that in no way the beta functions are small? We don't know, okay? In fact, if you had a situation like that, this would even contradict this idea, okay, that there is a proximate scale invariance. Imagine the theory exits here, and then you have a discrete scale invariance. After every, say, 2 pi in certain units, it goes back to itself, okay? Would be something very, very funny. Oh, please.
The strategy of the 4 dimensions that like any UFT is like pretty close to the CFT?
Well, the strategy is that it's very simple. This assumption that you're close to the CFT fixed point basically reduces the problem to the 2-dimensional one. If you're not close to the fixed point, you have to consider 2, 3, and 4-point function of t, and that's complicated to see. To say that t is 0. But if you are close to the fixed point, then at leading order in an expansion in the beta function, the quantity you have to consider is the 2-point function, and you deduce the 2-point function must be 0 at that order. Okay, that's basically the strategy. If you want, it's like in 2 dimensions. You prove that the TT correlator is 0. So that's the strategy. Just reduces to the. If you want, if I start doing the 2-dimensional case, then we go. If you want, we can discuss that later. Okay, if you want, that can be discussed later on in the discussion session. But this is the phenomenology talk. don't drag me. You see, you're string theorists, okay? Please.
So you mentioned a little bit before that, like, do we know anything about the limit in that case?
I know that in non-relativistic theories there are cycles. There's this Efimov cycles. It's like it's the effective theory that describes the interactions of 3 non-relativistic particles, the interaction of relativistic particles in the limit where the scattering length goes to infinity. Close to that point, you can describe the system in terms of a cycling. Yeah, that was studied even by Wilson, I think. It's.
So just to be clear, so a bare master is like part of the free sector.
There's no such thing as a bare master. I mean, everything is physical. Okay, there's a bare. There's a master here. There's an input parameter, and then there's something you measure. Okay, and that what you measure is a function of your input parameters, and that called the bare master if you want the input parameter. Yeah.
I don't know, but I mean, for example,
Yeah.
The tachyonic mass of Higgs, for example, like that's some constant. Anyway, so this here was considered because usually when you say the free part of the theory, you can consider the mass term as well, but in that case, you wouldn't have the scaling values.
No, the free part, free massless. Sorry, free massless.
Okay.
So sorry, free massless, free massless. Yeah, free massless. Sorry. Free massless. Free massless. Sure. Free massless. Actually, I have to speed up. Okay. Notice something very interesting that happens when you have this situation. And I will just say it in words. If I write, then it's going to take more time. So let me say it in words. You have a fundamental scale. You have an infrared scale, and you flow. Okay, basically the physics, okay, is the physics of a fixed point that is conformal, and then as you flow down, you can picture the mapping between the UV and the IR in terms of energy flow, and you can compute your observables in the infrared by first solving the energy flow. And as you know very well, in a reasonable conformal theory, the number of scalar operators of dimension strictly or equal than 4 is finite. Okay, in fact, and therefore, while the set of operators of dimension bigger than 4, the relevant operators, is infinite, and that set is precisely what contains all the complicated structure, all the information about your ultraviolet dynamics. Well, the irrelevant operators, as you flow towards infrared, their coefficient effectively flows to 0, and as you approach the infrared, only a finite number of coefficient remain important. Okay, and so it is to say that as you flow towards the infrared, the description simplifies. Okay, it's the same phenomenon that you have when you look at somebody, and then you start going back and back and back, depending whether you like or not like the person. Eventually, the person will be a point. Okay, and everything will be simplified. Okay, it's the same situation. In fact, it will be a point. It will be a point, and even no matter what the shape of the person, this point will have an accidental additional symmetry, SO3. Okay, and this is very much intrinsic in the process of simplification when you go to long wavelength or low energy. Within the number of operators that are relevant or marginal, there may not be any operator that transforms under a given global symmetry. Okay, so what you can have is what we call accidental symmetries. Just the very existence of a separation of scales implies simplifications and the origin of accidental symmetries. Okay, and this is a very, very important fact to keep in mind when we think of quantum field theory. This is more in Europe, but already when I was studying physics, the idea of renormalizability as truly an important principle without which you cannot do anything is totally dismantled in this view. Okay, renormalizability is to say the description of the Lagrange in terms of operators mentioned is less or equal to 4 is just an emergent phenomenon whenever you have a separation of scales. Separation of scales is the essence for the relevance of renormalizable theories in our description. Again, this is a concept that was formalized by Wilson, and some of the important steps to make it more quantitative, according to our ordinary understanding of renormalization, was again done by Joe in the 80s. Okay, I also do it when you're not around. I also say these things when you're not around. So the basic idea that quantum field theory is simple, has symmetries, because it's fundamental, from this perspective, is totally wrong. Okay, quantum field theory is simple, has symmetries, precisely because it's not fundamental. Okay, because we are looking at things from far away. Okay, so let me see where I am. Okay, now a very important notion in all this is played by symmetries. Okay, and if you want, it's important because symmetries can arise as accidental symmetries. Okay, but let's consider symmetries in general. Or perhaps I'll do this. Actually, do this. So let me come to the second part of this lecture, that is to say, symmetries, selection rules, and naturalness. So in quantum field theory, we are faced with two classes of symmetries, gauge symmetries. And here, as you know, these are not symmetries in the ordinary sense. They are redundancies that are needed to write in manifestly local Lorentz invariant way theories, field theories involving particles with spin higher than 1/2. Okay, and in that sense, gauge symmetries can always be viewed as exact. Okay, you make gauge fix, but you can always write your theory in a form that preserves the gauge symmetry. If you want, if this gauge symmetry is broken, if you break it, it just means that you're adding degrees of freedom. Okay, it's just you're now writing a drama with more actors. Okay, gauge theory is just, the goal of gauge theory is to write a minimalistic drama. Okay, and apparently nature likes to do that. Okay, and then we have global symmetries. As far as we understand, in fact, you understand it better than me, in string theory, okay, there are no global symmetries. I don't know how this statement is. But, okay, there are no global symmetries, but under many circumstances there can appear in string theories and in ordinary quantum field theory approximate accidental symmetries, okay? Like in string theory, when you compactify, you have for some reason, you get a slightly bigger compactification manifold. Yukawas can come from world sheet instantons. And if particles are localized at different places, you can get exponential suppression of Yukawa coupling, and you have an emergent effective chiral symmetry in the low energy Lagrangian. I mean, you can have global approximate symmetries. Okay, these are things that you have quite often, and they play an important role because they play an important role in our understanding observables. Okay, and the way global symmetry is global approximate. Okay. Are the magic word by which symmetries are affecting our view of physics is selection rules. Okay. Well, just to give you an idea of what selection rules are, okay. So the standard example is in atomic physics. So selection rules are the set of. It's just an application of the Wigner-Eckert theorem to estimate how a given observable that has certain transformation properties under a given symmetry will depend on a parameter, an external control parameter that is also transforming under that symmetry. Okay, so the canonical example is in atomic physics, in the interaction of atoms with the electromagnetic field, whether static or dynamical. So, for instance, in the static case, atom in electric field, constant electric field, the Hamiltonian will be given by the zeroth order Hamiltonian minus the interaction of the dipole operator times the electric field. And as a result of this perturbation by an external vector, the energy eigenstates will not have definite angular momentum. You will have mixing, okay? And the mixing of states with different angular momentum in the limit where E is small, sufficiently small, and what that means depends on the feature of the atom you are considering. When E is sufficiently small, the mixing will be controlled by the suitable power of E associated. Okay, let me give you an example. Okay, if you have, say, you have So how can I define the mixing? Let's say you have an energy eigenstate alpha in the presence of an external field. The mixing, let's say a definition of a mixing between states with different angular momentum, J3, okay, given alpha is a function of E, can be defined to be the following quantity: J prime 3 is just the overlap, okay. Okay, so this is just picking up the components in the eigenstate alpha associated with J and J prime, and you applying the Wigner-Eckardt theorem. There are various ways to do it. You can do it just by seeing which order in perturbation theory you need to go before this quantity is non-zero. Okay, you can prove that this thing goes at least like E, the electric field, to the J minus J prime. Okay, so you need at each, to mix levels that have angular momentum different by 1, you need to insert one vector E, two vectors, and so on and so forth. Okay, so that's an example of a selection rule, and here E is our small parameter. And of course, if it can happen that you do this estimate and then you go and look at your physical system and you find that the mixing is much smaller, well, presumably that means that we have missed some other symmetry, for instance, parity. Okay, and you go back and you try to account for it. And in the vast majority of cases, this is why we like physics. Okay, we can use these tricks to quickly estimate the size of physical quantity, very much like we were very excited when we learned to do dimensional analysis to estimate like the frequency of the pendulum or stuff like that. And dimensional analysis is just one variety of application of selection rules for dilatations. Okay, you perform dilatations of the units of measure of all your possible observables. Okay? That's just dimensional analysis. Okay. So, however, there can be situations where for some reason this quantity is much smaller than the selection rule suggests, and there's no symmetry we can look for to explain for that, and we call the situation a tuned situation. In other words, for some reason we concocted our system, or we went through the periodic table and we chose in this periodic table that 1 out of 100 elements for which this coefficient here, instead of being 1, is 0.01. Okay, they say they are distributed, there is 1 for some reason. Okay, so the Mendeleev table is a sort of landscape. Okay, you can go around, you can pick. I mean, this is really condensed matter done by somebody who doesn't know anything. Okay, so but you can view it this way. Okay, and but normally you don't get any dramatic effect. You don't get 10 to the minus 10. You can get 10 to the minus 20. Okay, at least I don't know of any example. Okay, so this is why selection rules are famous. Okay, now this reasoning applies equally well to quantum field theory. Okay, and it's at the heart of the notion of naturalness that was introduced by Toft in the 70s. Okay, so in quantum field theory, we can think, just to simplify a little bit mentally what we want to do, you can think of the theory at the scale of the IR scale. Okay, and you want to compute some observable having to do with physics at this scale or below. Okay, so that you're far away, or even far away from the cutoff. Just not that this is necessary, but just to concentrate on a finite number of couplings. Okay, perhaps if the experimental precision is not good enough, you can forget all the relevant ones. Just focus on the marginal and the relevant if they exist. And we will later on try to understand better. But so let's so there's going to be at the given scale we're considering, our quantum field theory will have a certain number of parameters, and we can view oftentimes In fact, basically always, we can always view these parameters as the expectation values of fields that we call spurions, okay, that somehow transform under the global symmetries of our system, restoring them formally. I think the notion of couplings as fields, if I'm not, I think that Nati Seiberg used it in his lectures, right? So you're even familiar with superfields, coupling as superfields, not just fields, okay? So under the circumstances, there's going to be some, that's often the case, you have a global symmetry group G, and under this group G, these couplings transform in a given way. And assuming there's a certain amount of smallness in these couplings, okay, here I'm being a little bit fuzzy in the discussion, okay? Then under if you can treat them as small and there is some conditionaliticity, but that's not really needed, you expect observables, this is just to simplify the discussion, can be written as polynomials in these couplings, okay? That's often the case when you have like flavor transitions, you have contributions from Yukawa couplings, mixing angles, and so on. So polynomials in these quantities. And so given the coupling and given a certain observable, okay, this observable will, you can compute this observable in this effective theory, and in a sense by an incarnation of Gell-Mann's dictatorial principle that all that can happen in quantum field theory must happen, okay? The system will explore all possible trajectories, all possible ways to contribute to this observable. So you will have that is like the double slit experiment. You will have that the observable, that it's the sum over all possible contribution or amplitudes of individual amplitudes, okay? And each individual amplitude or individual contribution to the observable can be written as some some coefficient Ci lambda I lambda I n to some power n I n n. Okay, so there can be some and the way these powers enter, okay, is fixed by symmetry. And the simplest possible symmetry you certainly can use as a and this fixed by symmetry and is fixed by transformation properties of this observable. And the simplest possible symmetry that you normally use in this game is, let's see whether you're following, scale invariance. Okay, it's just dimensional analysis. Okay, dim O is equal to the dimension of this lambda, okay? So that's just, dimensional analysis is just applying the selection rules of dilatations, okay? And very much like in the case before, you can think of two situations. You can think of the situation where if there is a disparity of contributions, they have different sizes, if there is one that is bigger, there is one that is bigger than all the others, if O experimentally is of the order of O maximum, which is equal defined to be the maximum of I of the OI, I'm formalizing things that are ridiculous. I mean, it's perhaps ridiculous to formalize these things, but let me do it, okay? So if the experimentally observed quantity is of the order of the maximal contribution, then you say, okay, then the situation is natural. If, on the contrary, what you measure experimentally is way, way smaller than the maximal contribution, then there are two options. One is that you have forgotten some symmetry, that there is some correlation between, there is something that you're really missing, that some of these amplitudes are not independent, they are correlated to one another by some other symmetry that exchanges the various lambdas, okay? And you will have to understand that, and perhaps you will find that when you take that into account, you end up in the first case, and then the situation is again natural. Or it could happen that you cannot really think of a symmetry that realizes that, and that this just happens because two or three or more of the maximal contributions just conspire to cancel one another, okay? And the situation is not satisfactory, okay? And this is what we call a natural situation. Okay. So now this is the case where you are. Let's say that I just consider the simplifying situation where you are in a theory with a finite number of parameters. You're just forgetting all the irrelevant ones. But you can apply the same reasoning to the very theory itself. Okay, you can apply the same reasoning. Let's say you have your cutoff here. Okay, you can apply the same reason, and here you have your theory is defined by some approximate CFT plus sum over I, lambda I, or I. I mean, these are operators now. These are not observables. Let me put a hat. Okay, no, these are not. You have an infinite series of operators. Now, you can view these coefficients here, the coefficients of the operators of my effective Lagrangian, themselves as observables. Okay, as observables. I mean, they are the observables of my infrared theory. I can compute everything using them, modulo, redundancies, or stuff like that. But you can view themselves as observables, and they are presumably. In our idea of effective theory of quantum field theory as effective functions. Okay, of the parameters of the more fundamental theory. Okay. And then you can ask yourself, very much like in that case, whether given a certain theory that is given to you by nature, I mean, experimentalists have measured, okay, there are the coefficients there, and now it's up to you to look at this Lagrangian and try to smell it, to see what's the deal with it. And one question you can ask yourself is whether any pattern in the structure of this set of couplings lambda I, for instance, some smallness of some classes of couplings, is compatible with selection rules of some hypothetical symmetry that you can assign to the more fundamental theory. Okay, so whether you can explain any features in this set of couplings, very much like you will explain it here. Okay, here in a natural case. If you are in a natural situation, then the size of your exponential quantity is really controlled in a simple way by the size of your lambdas. And if this observable becomes small, that's in one-to-one correlation with the lambdas becoming small. While on the other hand, in the case of a natural situation, the observable may be small, but the couplings themselves that are responsible, that in general break the symmetries that control that observable may not be small, and that's unnatural. So you can ask yourself whether a given Lagrangian is satisfying this criterion. And this criterion is the Toth naturalness criterion, okay? Please.
Sorry, what assumption did you make about the CI?
Yeah, here the assumption I made here is that the CIs are order 1, okay? In specific cases, let's say if you have loop diagrams, they are 1/16 pi squares, but they're order 1. They're not real. They're not really these parameters, okay? They just come from the. If you want, if I have a strongly coupled CFT, these CIs are from the 3-4 point function of the CFT, and These are just numbers, okay? Of course, it could be that the CFT itself has some tiny numbers in it, okay? And that's the CFT itself has been tuned, okay? You see, this thing goes into this slippery slope, okay? If you have a landscape of CFTs, there could be cancellations there at that level. So, yeah. You could choose, okay? If you have a Mendeleev table of 10 to the 8 million CFTs, then you can choose some cases where. There can be many. There can be more than one. There can be more than one. Yeah, the maximum is like Mont Blanc and Montrose. They're more or less the same. Okay? It can be several peaks. Okay, comparable. Okay, not necessarily. Okay. So notice that in this situation, and given the discussion before, I think it's clear that the smallness of any parameter of class of parameters, okay, if it's way small, for some reason it's very small, must be associated with the presence of a symmetry. So in other words, in order for this to be natural, okay, that's precisely according to this, okay. A small, under these circumstances, under the natural, under the first class, that's to say a natural situation, a small quantity, a small observable is associated with small parameters breaking the specific symmetry. Okay, so the natural situation here is of naturalness. Okay, smallness of lambda I. So if you want, this is a criterion. Okay, it's an ideology. If you want, that's precisely what it is. Okay, smallness of given parameter or class or set or subset must be associated, is always, okay, with symmetry. That is to say, even more in a let me say it necessarily, if you want, when this a class of a parameter or a class of parameters can be naturally small, this necessarily implies that when you set these parameters to 0, you've gained an additional symmetry. Okay, so that's tough naturalness. Let me give you a feeling for that. Okay. Let me show you how we argue, we model builders, phenomenologists, in this. Okay. So I'll give you an example. An example is, let's take for instance, a theory where there is two Weil fermions. Let me call them like two neutrinos, u1 slash u1 plus u2 slash u2, and then you have a scalar d phi square, and then you have interactions. Let me forget for a moment the mass of the scalar. Okay, and then you have interaction like lambda 1 1. You have phi. You have interaction with 1 1, 1 2. Okay, so you have sort of you have interactions, and then a question you may ask. Okay, let's say given experimentalists have measured this Lagrangian, and they've measured lambda 1 2 and lambda 2 2 for some reason, and the question is how small can we tolerate lambda 1 1 compatibly with the criterion of naturalness I introduced before? Well, let's see what symmetries we can think of. Okay, and the symmetry we can think of is just a u1 cross u1, under which u1 rotates and u2. I mean, this rotates. This is the u1 number. This is the u2 number. Okay, and under the symmetries, let me just say it here: u1 1, u1 2, u1 u2, lambda 1 2, lambda 2 2, lambda 1 1. Here you have 1, 0, 0, 1, 1, 1, 1, 2, 2, 0. Okay. So according to this symmetry, okay, we can put together a combination of lambda 1, 2, and lambda 2, 2, and form an object that has the same quantum numbers of lambda 1, 1. Namely, lambda 1, 1 transforms. I don't know how to say it. It's equivalent from the transformation property from the symmetry point of view. I'm not yet saying quantity. Oh, sorry, 0. Sorry, yes, good. So lambda 1, 1 has the same quantum number as lambda 1, 2 square, lambda 2, 2 star. Okay? And so grossly you would think, well, if I measure these two guys, I would expect that on general grounds, lambda 1, 1 cannot be smaller than a quantity of this order, give or take coefficients of order 1 or pi's and stuff like that. And can you be sure of this, or can you test this hunch, or this whatever call it, no matter how you want? It's probably time to use this terrible tool. No, probably I can do this. I still have space. So, and you can check your guess by looking at quantum corrections within the effective theory. Okay, so a fortiori, these are subset of the quantum corrections. You may be missing even bigger effects, but certainly this exists. And if you take, for instance, this diagram like this, this goes out. This is phi. This is 1. This is 2. This is 2. And this is lambda 2. So this is a lambda 2, 2 star. This is lambda 1, 2. This is lambda 1, 2. Okay. And this gives you a correction when you flow from the RG from the UV to the IR. It gives you a correction to lambda 1, 1 that is of order 1 over 16 pi square. Lambda 1, 2 square, lambda 2, 2 star, log of lambda over mu, where mu is the infrared scale. And of course, this, in a sense, may have nothing to do with what I was telling you before about the ultraviolet theory, but certainly if an effect of this type exists at scales of order of lambda, it's hard to imagine that they will not exist. I mean, in the theory, and anyway, there could even be bigger effects, okay? But certainly this is a minimal effect you expect to have. So it's according to naturalness, you declare that you don't expect lambda 1, 1 to be significantly smaller than this. Modulo factors of pi cannot be 30 orders of magnitude smaller than this. Okay, it's hard to understand. Okay, so that's an example. And as a little exercise, you can consider this other theory. Oh, here I neglected the case of scalar mass. I will discuss that in a moment. You can consider these other examples where you have only scalars, and you have let's forget the masses for a moment, and you have the analog 1, 1, phi 1 to the fourth, 1, 2, phi 1 square, phi 2 square, plus lambda 2, 2, phi 2 to the fourth. Okay, here you don't have any chiral symmetry. Still, I am willing to say that I can find a symmetry and by similar arguments as the one I just made. I can say that lambda 1, 1 must be less than order lambda 1, 2 square. Modulo factors of pi. There's a symmetry protecting that, explaining this relation, and it's just a little exercise to find it. Let me tell you that just for fun, that free field theory has infinitely many symmetries. Okay, this is where you have to dig. Okay. Okay. So and these are the working. If you want, this is the practicing that we model builders use. Okay, that like it or not, this is the way it works. And there is one very important there's one very important thing that I want to really emphasize, and I really see that I'm already behind my schedule very, very dramatically. But let me tell you, let me give you a slogan, okay, right now. So tough naturalness. So if I had to explain tough naturalness to people in condensed matter, how would I go about and tell them, oh, there is symmetries, and they say, well, I mean, who ordered these symmetries, okay? So, I mean, okay, if these things are small, then this is small accordingly, but why were lambda 1, 2 or lambda 2 too small in the first place, okay? If you want, this is maybe the symmetries you're assuming here, the structure of the coupling is self-consistent. Okay, a structure of coupling compatible with tough naturalness may be self-consistent, but the fact is, of course, and that's way, way better than a structure that is not self-consistent. Okay, that's very implausible, but that doesn't yet explain it. Okay, where does the symmetry come from? Okay, why is it there? And of course, after all I told you before, we have sort of answer for that. The idea is that the symmetries may arise as approximate symmetry from the previous life of our theory. In other words, from the structure the theory has at scales even shorter, you can think of at scale higher than lambda, there's been another layer where lambda is the infrared scale, and there's a bigger lambda prime even above, and in the flow between lambda prime and lambda, you have had this purification, simplification of the theory, and the accidental symmetries have emerged. In other words, it could be that one view is that the accidental symmetries, the approximate symmetries of today are the accidental symmetries of tomorrow. Okay, and an example of this is, for instance, think of Fermi theory. Fermi theory is the theory that describes the interaction of, well, at the time he was looking at neutron decay, but the Lagrangian describing the interaction between muons, electrons, and neutrinos. Okay, there's a Fermi interaction for Fermi interaction. There's only one chirality of neutrino. The electron and the muon have a mass, but the neutrinos don't have a mass. Okay, and people I don't know what people were thinking in those days. I mean, the neutrino is massless. Okay, and Majorana probably would have said, okay, why is it massless? Okay, I can write a mass for sure. I can certainly write a mass, a Majorana mass. Okay, and then probably they said, well, okay, there's a symmetry. There's a very important symmetry of nature, lepton number. The only mass you can write down breaks lepton number, and lepton number is a fundamental symmetry of nature. Let's impose it, and that's it. So, in fact, that's not even approximate. That's truly an exact symmetry at that stage. But what's the origin of lepton number? Okay. Wait a few decades, go to the standard model, and now you are at the next layer. You're looking at the theory at scales above the weak scale, and what do you have in this theory? If in this theory now the neutrino is part of a bigger structure, an SU2 doublet, in order to generate a mass according to the presence of this structure, you need to have the neutrino talk to the Higgs. Okay. And the Higgs is a doublet, and the only way to have the neutrino talk to the doublet is via an irrelevant operator. Okay, so neutrino mass is H Higgs lepton doublet square divided by some scale. Okay, it's probably close to the gut scale, 10 to the 14. In fact, this is another remarkable thing, that what we observe in neutrino masses is compatible with this scale where everything seems to want to go. Okay, a scale that is a few decades between 10 to the 14 and 10 to the 18. So, okay, so that's an example of, and similarly, if I will say it in a moment, I'll probably say it tomorrow. Okay, I'll say this later on. Okay, so, but a side example like this, there are in theories. Let me give you another example that is very, very important for all that follows. I think I can make it. I'm afraid I have to do this. Okay. Now let's see how because yesterday when I was seeing you guys doing it, I was not happy from the way you see. In fact, I'm even worse.
It's fun.
Because I was saying, oh, they're keeping too much water. But it's the same. I'm doing exactly the same. So. That's fun. Oh. And then. It's so satisfying. Yeah, too bad that what I'm gonna write now is crap. Sorry. That's always the case. It's like it's the beauty, and so now we come to an example. Okay, that is the centerpiece, if you want, of all gibberish on BSM. Let's take a theory of a scalar field. Okay. Like 5 to the 4th, okay? We can add a mass term, we can add a quartic interaction, we can add more, okay? And now the relevant question is, how small can we tolerate? Let's say, given lambda, how small can we tolerate M? Compatible with naturalness, okay? And here, what is the relevant symmetry? The relevant symmetry is a shift symmetry in the limit where lambda, let's forget this, let's forget M, in the limit where lambda vanishes, okay? Of course, everything else should vanish, okay, all the other terms, but let's focus just on lambda. In the limit where lambda goes to 0, oh no, this doesn't go up. Now I'm stuck. We acquire a symmetry, a shift symmetry, okay? So phi is what you would call a Goldstone boson, okay? That's the symmetry. And the symmetry forbids any interaction that does not involve derivative of phi, okay? So according to the symmetry, phi must only have derivative interaction. Now, phi to the 4th is a non-derivative interaction, and then by Gell-Mann totalitarian principle, this lack of invariance under derivative interaction will propagate everywhere in all possible ways, okay? And you can estimate, very much as we did before, what you expect. You would expect generically, naively, okay? It's not easy to do it right away with selection rules, but let me just do it in the correct way, although the discussion is not as neat as that. You expect that this M will have to be, certainly, if lambda is non-zero, there's some power of lambda that will intervene in controlling the size of M, okay? But lambda is dimensionless, so you must introduce the other parameter you have in your theory. Remember, the scale lambda is a physical scale, okay? So according to the selection rules of dilatations, you expect this parameter to be there precisely this way, okay? And so you expect that this is basically the relation, okay? The mass should be bigger than that. And you can check that this is precisely what you obtain when you compute one-loop corrections in the effective theory. This one-loop correction is not calculable within the effective theory, but it indicates what to expect, right? You get a correction to the mass that goes like lambda over 16 pi square, some integral dp square, that, of course, the integral is not calculable within the effective theory. Normally, this is called the quadratic divergence. I don't want even to insist on that. Okay, we don't know the coefficient, but clearly there's no reason why this should be not equal to of order lambda square. Okay, that's, if you want, selection rules tell us that this should be of order lambda square. There's nothing else. Okay, there's nothing else. In particular, you cannot use scale invariance. Okay, because scale invariance is broken by lambda itself. Okay, so normally, often you have statements that you could use scale invariance as a symmetry to protect the mass, but in the relevant case, scale invariance is broken in the maximal possible way by the presence of a physical cutoff. So this is what you expect, and this is the well-known Wilsonian horror for massless, for light scalars, okay? And that's well known to people working in condensed matter laboratories, where in order to set their system or equivalent system to the point where the equivalent quantity of the scalar mass is zero, they have to hire a very good lab technician, like say in the analog in 3 dimension, the Ising model in 3 dimension, that's water at the critical point. You really have to tune your parameters of pressure and temperature to be precisely at the critical point in order to have this parameter vanishing. In other words, you need to tune, okay? Unless lambda is very, very small. In that case, you have a Goldstone boson. But if lambda is very, very small, the interaction of these objects are very, very different than an ordinary scalar. It's only coupled derivatively, okay? I'm afraid I am done, okay? Because now I was at the moment of making my point, okay? After all this long discussion, and the point I will make it tomorrow, okay? It's already clear where I'm going, okay? In terms of time, okay? The point I want to make now is the question I want to ask now, and this question is invited by this case here, is okay. I'm done. I finish in 2 minutes. I just say this thing. No, I'm just saying. I'm just saying that from the point of view of the effective theory, the next layer, the infrared scale itself, okay, this IR scale here, lambda IR, is a function of the couplings at the cutoff. Particularly, will be some combination of your original parameters. Could be in weakly coupled theories, just basically the mass of the scalar of some field you have there. And the question is whether this quantity, which is just a particular combination of parameters, whether its smallness is natural according to the criterion I was discussing before. And you can identify overall 2 situations. I thought he had many more. You had like 6 or 8, but at least in let's say that in theories, but I think we can go back on that. In the theories that are relevant for phenomenology in relativistic quantum field theory, there are basically 2 situations where this separation of scale is natural, okay? And I call these 2 scenarios, one is marginality and the other is symmetry, okay? And these 2 cases, that are the only 2 we have been able to think of, correspond also to the 2 scenarios to address the hierarchy problem that we mainly been able to think of, that is compositeness and supersymmetry. And that's it. Okay, thank you.
Questions? Is there a way you can imagine f squared and lambda they're transforming to restore symmetry?
No, I don't think there's any way. I don't think there's any way. No. But think of it. Think of it. If you find it, that it would be. I don't think there is any way. I mean, you need something that. Let's say that. Well, in general, you can have a situation where you have another parameter that transforms. So let me put it this way: yes, in a sense, but that's not interesting. You have lambda, okay, and then you have phi plus another parameter, call it a vev, to the 4th, and this shift and that shift. That's it. Okay, in a sense, you're cooked. Okay, this parameter, okay, formally you have the symmetry, but a parameter that introduced that restores the symmetry is not small. It's a dimensionful parameter with so the only scale you have is lambda. This parameter is expected to be lambda, unless this parameter itself transforms under some symmetry.
So why is it considered natural for the couplings to be afforded 1 1 and why does that?
Being a coupling of order 1 doesn't mean anything.
Okay. Right.
Depends on the fact that you have chosen natural units. H bar equal 1. If couplings were of order 1, then loop expansion parameters would be of order 1, strictly speaking. So let me say, couplings, I mean, you should look at loop expansion parameters. Loop expansion parameters are the truly physical quantity that is independent of the normalization of H bar. When you rescale H bar in your Lagrangian, so you have the path integral, you have d phi e to the is over H bar. Okay, rescaling H is like rescaling the coupling in such a way that this quantity is invariant. So the couplings are not that, they're not of order 1. They happen to be of order, say, in the standard model, they range from, at the weak scale, they range from, for the electron, this is 10 to the minus 10. To the top, this 10 to the minus 2. So you're asking me why?
Yeah, I mean, basically, why?
Why this number? No, but that's a good question. Why is the loop expansion parameter? Why is the loop expansion parameter 1 in 100? That's a good question. Why? String theorists. This is a question for string theorists.
I know that's the hierarchy problem. Basically,
No. It's a question for string theorists. Imagine. Sorry, should I stop or?
Take a few minutes to answer the question, then we should go to break.
Okay, so it could be that this 1 over 100, over 30, say for the gauge coupling, is 1 over the log of the separation from the string scale and the weak scale. So imagine you have at the string scale, you match onto a theory that is infrared free. But the string scale is maximally coupled. The dilaton is stabilized at the self dual point. Okay, the string theory is strongly coupled irremediably. There's no perturbation theory, and but it happens that and then couplings emerge as large, or their loop expansion parameter are of order 1. But then you have say 4 pi over alpha in the mu IR is 4 pi over alpha mu UV plus some coefficient of order 1 that is the beta function coefficient log mu IR mu UV. Okay, that's and this is of order 1. So now if but that's again if this is 1, because the theory is strongly coupled there, if we know that the separation here is, say, 10, 20 orders of magnitude, then this loop expansion parameter here is 1 in 20. So the 1 in 20, 1 in 50 may be just the result of that. Now the question is, if all couplings are of order 1, where the hell is this big log coming from? Okay, because then everything is there. So then that's okay. Perhaps some SO32 is. Perhaps there are some large numbers in the structure itself of the theory has some n, but n of order a few, and there is some coupling that at that scale starts of order 1 over 20, so like the QCD coupling, and then that one grows, and when that one becomes order 1, then you have gone again through about 20 orders of magnitude in the log. So that I'm sorry, I cannot do any better than this, but that's not my fault. I mean, so that is what could account for the size of the couplings. Then the Yukawas, it's a different story. But
you didn't need string theory after all. You did not need string theorists after all.
Yeah, I mean, well, okay. If you're happy with that, then you don't need it. depends on your.
Okay, move on to break, and thank you.
I mean, it's hard to make this thing.